How's it going, guys? Today in this video, we're going to be finishing up 10.2, and we're going to be talking about dividing rational expressions and also about closure. So when we're dividing rational expressions, it's actually going to be very similar to what we learned in the last video or in the last day with multiplying rational expressions. We're just going to have one or two extra steps beforehand. So when it comes to dividing rational expressions, the very first thing we're going to do is we're going to set up the division problem to actually be a multiplication problem by the reciprocal of the second expression. So that sounds like a lot, but when we do an example, you'll see it's really not that bad. After we do that, we're going to factor the numerator and the denominator. It won't be a rational expression problem without us actually factoring the rational expression. Next, we're going to find excluded values of both denominators and the numerator of the second fraction. And we'll see why we have to do that as well when we go over an example. After we factor out and, find the excluded values of the problem, of the expressions, we're going to multiply the numerator and denominators. And after that, we're going to cancel common factors and simplify the expression as much as we can. Okay? So let's go ahead and do a problem. On number one, we have x plus 7 squared over x squared divided by that other rational expression. So when we're dividing rational expressions, like we said, we're going to change this division problem into a multiplication problem by finding the reciprocal of the second expression. And really, that's just a fancy way of saying we're going to flip it over and make the bottom to the top and the top to the bottom. So if we rewrite this as a multiplication problem, we get x plus 7 squared all over x squared, multiplied now instead of divide by x squared plus x minus 2 over x squared plus 9x plus 14. We're just flipping the second fraction, and then we're changing the division into a multiplication problem. Okay? And after we do that, the next thing we're going to do is we're going to factor the rational expression. The first expression, or the first fraction, is already completely factored out. We're just going to rewrite it. As for the second expression, the x squared plus x minus 2, that's going to factor out into x plus 2, x minus 1. And all of that will be over x plus 2 over x plus 7. Okay, so now that everything's factored out, what we want to do now is we want to find the excluded values. So the excluded values of x are going to come from the denominator of the first term, the denominator of the second term, and the numerator of the second term. And why we want the numerator as well is because this x plus 2 times x minus 1 used to be a denominator of the original expression. X squared plus x minus 2 factors out into that x plus 2 times x minus 1. So if at any time the numerator over here, x plus 2, x minus 1 is 0, our original expression is also going to be undefined. So that's why we have to include the numerator of our problem over here in our excluded values, because it used to be a denominator in our original problem. So our excluded values are going to be 0 from the x squared, the negative 2 from x plus 2, negative 7 from x plus 7. We have another negative 2 from x plus 2, but we don't need to write it twice. And lastly, we have a 1 for x minus 1. So those are all our excluded values of x. All right, and now that we figured out our excluded values, we can finally multiply everything and simplify our expression. From here on out, it's just like multiplying rational expressions that we learned in the last video or in the previous day of class. So when we multiply these expressions, all we really do is just mash everything up into one big fraction. So we have everything on the top right next to each other, all over x squared times x plus 2 times x plus 7. Okay? And then from here, we're going to figure out, we're going to see common factors from the numerator and the denominator and cancel whatever we can cancel out. So we have an x plus 2 on the top and bottom. We can get rid of those. And we can see we have an x plus 7 all squared. Remember, that means it happens twice. X plus 7 all squared is the same thing as x plus 7 times x plus 7. So we can get rid of one of those x plus 7s on the top, and get rid of the x plus 7 on the bottom. And when we do, we're left with x plus 7 on the top times x minus 1 all over x squared. We can't reduce it anymore from here, so this right here is our simplified version of the expression. Okay? So now let's go on to number 2. And number 2, we're going to do a little quicker. For the first one, we have 6x all over 3x minus 30. If we rewrite that, we get 6x all over 3 times x minus 10. 3 is the GCF of 3x minus 30, so we can just rewrite it as 3 times x minus 10. And we're going to multiply all of that with the x squared minus 10x. That's now going to become on the top. It's going to go to the top, and if we factor it out, or factor out the GCF, we're left with x minus 10. And now that 9x squared minus 27x minus 36 is going to be on the bottom, and it also has a GCF of 9, so we're left with x squared minus 3x minus 4. So we figured out a reciprocal, and we just pulled out the GCF. Okay? And then from here, what we want to do is we want to factor out each expression as much as we can. So 6x all over 3 times x minus 10, that's factored out. We can just leave it as it is. And for the second expression, the x times x minus 10 is as factored as it'll get. And then the 9 times x squared minus 3x minus 4, that's going to factor out into 9 times x minus 4, x plus 1. Okay? And so from here, we're going to figure out what our excluded values are going to be. So our excluded values are going to be x minus 10, or just 10. The value from x minus 4, which is 4. The value from x plus 1, which is negative 1. The value from this x, which is 0. And the value of from this x minus 10, which is also just 10. But we already have it over here. We don't need to write it twice. And remember, the reason why we're including the x and x minus 10 is because this x and x minus 10 used to be on the bottom over here. And if x squared minus 10x is set equal to 0, our original expression is going to be undefined. So that's why we need to make sure the x times x minus 10 cannot equal 0 as well. Okay? So these are all our excluded values of x. And now that we found our excluded values of x, we can actually multiply this now and figure out our simplified version of the expression. So if we multiply the top out, we get 6x squared times x minus 10. We're not going to bother foiling anything out. Just leave it as factored as you can. All over 3 times 9 is 27 times x minus 10, x minus 4, and x plus 1. Okay, so that's our multiplied version of the expression. And now we're going to see if we can reduce it or simplify it any from here. So I see I have an x minus 10 on the top and the bottom. We can cross those out. And then I also see I have a 6 and a 27. That can reduce down into 2 over 9. They're both divisible by 3. So I divide each of them by 3, and I'm left with a 2 over 9. So I'm left with 2x squared all over 9 times x minus 4, x plus 1. I can't reduce it anymore from here, so this is my simplified version of the expression. Okay? This stuff really isn't that much different than multiplying by rational expressions, so what I want you guys to do now is I want you to pause the video and try to do number 3 and number 4 on your own. In a few seconds, I will post the answers on the board, and you can double check your work with mine. Okay, this is what you should have gone for number 3 and number 4. You can go over it on your own. You can pause the video, look over it, see what you did differently than I did, and double check your work. Okay? But other than that, we're going to keep on going. I want to start going over closure and what closure means. So, what this little excerpt on the top says is that a set of numbers is said to be closed or to have closure under a given operation if the result of the operation on any 2 numbers in the set is also in the set. So that's the explanation. That, like always, you'll probably understand it better when we actually go over a few examples. So we have this chart in the bottom of your notes over here, and what we want to do is we want to see if each of these sets of numbers over here on the left, so the set of natural numbers, integers, rational numbers, and the irrational expressions, if each one is closed under any of these operations. Okay, so we're going to see if the set of natural numbers is closed under addition. And what that means is that I should be able to add any two natural numbers. And when I add any two natural numbers, I should always stay in the set of natural numbers. All right, and in this case, no matter which two natural numbers I choose, and I add them up, I'm always going to get another natural number. So that means the set of natural numbers is closed under addition. Because no matter which two natural numbers I choose, I'm going to get another natural number when I add them up. Also, I should probably tell you guys what natural numbers is. You can see from the chart over here if you want to. But the set of natural numbers is going to be all the positive integer values, starting at 1, then going to 2, 3, 4, 5, so on and so forth into infinity. That's the set of natural numbers, okay? So 1, 2, 3, so on and so forth to infinity. That's the set of natural numbers, okay? And now for subtraction, the set of natural numbers will not be closed under subtraction, and that's because, let's say I choose 2 and 1. 1 minus 2 is going to be negative 1. Negative 1 is not in the set of natural numbers, so that means the set of natural numbers is not closed under subtraction. I put closed, it should be not closed. Now we're going to see if it's closed under multiplication. The set of natural numbers will be closed under multiplication. That's because I can choose any two positive integer values, and I'm always going to get another positive integer value. Okay, so it's closed under multiplication. And now for division, the set of natural numbers will not be closed under division, and that's because I can get fractions with some division problems. Think 3 and 2, 3 divided by 2 or 2 divided by 3, it really doesn't matter. That's going to give you 2/3 or 3 over 2. Regardless, it's going to give you a fraction. Fractions are not a natural number. It's not a whole positive number. So that means it's going to be not closed under division. And now for the set of integer values, well, we're going to look at the set of integer values anyway. Remember, integers are going to be any positive or negative whole number, including 0. It's like -2, -1, 0, 1, 2, so on and so forth on both sides. It goes from negative infinity to positive infinity. It's every whole number, including 0. So the set of integer values is going to be closed under addition because I can choose any two integer values at once. If I add them together, I'm always going to get another integer value. So it's closed under addition. Closed under addition. Same thing with subtraction. No matter which two integer values I choose, I'm going to get another integer value. Multiplication is also going to be closed under, our set of integers is going to be closed under multiplication as well, because no matter which two integer values I choose, I'm going to get another integer value. For division, it's not going to be closed under division, and that's because it runs into the same problem the set of natural numbers does when it comes to division. I can get fractions, and fractions are not part of the integers. For instance, 3 and 2 again. 3 divided by 2 gives you 3 over 2. 3 over 2 is 1.5. 1.5 is not in the set of integers. So it's not closed under addition. Under division. Now we're going to talk about the set of rational numbers. The set of rational numbers is just any number that can be written as a fraction. Okay? And that does include every single integer value because, for instance, 5 is an integer, but it can also be a rational number since 5 is the same thing as 5 over 1. So the set of rational numbers is any number that can be written as a fraction. So now we're going to see if the set of rational numbers is closed under addition. I'm going to talk about this in fractions, but remember, fractions does also include integer values. So if I add any two fractions, I'm always going to get another fraction, right? Just find a common denominator, add them up, I'm going to get another fraction. So that means the set of natural numbers, or set of rational numbers anyway, is closed under addition. For subtraction, if I subtract any two fractions, I'm going to get another fraction, right? I just have to find the common denominator again, and I can subtract the numerators, but regardless of what that is or how complicated it might get, I'm going to get another fraction. So it's closed under subtraction as well. Now for the set of rational numbers under multiplication, if I multiply any two fractions, I'm going to get another fraction, right? I just multiply the numerator with a numerator, denominator with a denominator, and I'm going to get a new numerator and a new denominator, but it's still going to be a fraction. So it's closed under multiplication as well. Now for division, dividing fractions is very similar to multiplying, it's the same. Let me back up. Dividing fractions is very similar to multiplying fractions. That's what I was trying to say. You know, we're just flipping the second number, and then we're just multiplying anyway. But we're still going to be multiplying by fractions when we're dividing. And when we already saw that if we multiply fractions, we get another fraction. So we're going to be closed under division as well. So the set of rational numbers is closed under addition, subtraction, multiplication, and division. And now we're going to be talking about the set of all rational expressions. That's what we've been talking about for quite a while now. And by now you should have seen that the set of rational expressions, they're very, very similar to fractions, right? They're just very complicated fractions, right? Instead of having numbers only, we're going to have numbers and variables. But nonetheless, it's still basically a fraction, and it's just a fraction it's a function as a fraction, okay? Just think of it that way. So the set of rational expressions, because it's basically a fraction, is going to act very similar to normal fractions or just normal rational numbers. So it's going to behave the same way, closure-wise, in addition to, when we're talking about addition, subtraction, multiplication, division. That's what I'm trying to say. They're going to act very, very similar. So the set of rational expressions will also be closed under addition, since it's basically fractions, and we saw that fractions will be closed under addition. Same thing with subtraction, multiplication, and division. It's all going to be closed because the set of rational expressions behave very similarly to the set of rational numbers, because the set of rational expressions are just, for our purposes, they're just very, very complicated fractions. Okay, so they're going to behave very similarly to rational numbers with respect to closure. Okay, so right here it says state in your own words what it means for a set to have closure. I would suggest you guys do that on your own. I'm not going to say anything about it or write about it, but I would suggest you do it just because you can have a good idea of what closure means. And trying to just memorize this chart and do it on take a quiz or test that way is not going to do you any good, because this is 12 specific things to memorize, and it'll be a much better use of your time to actually understand what closure means and have it memorized that way, kind of understand it that way. All right. But anyway, that's the video, guys. Hope it helped, and that's going to be about it.